Hello, and welcome to this Amatech Land webinar. Now let me introduce today's presenter. With us today we have Chris Leonard. He is from Amatech Land. To read more about Chris today, please look at the speaker bio window right next to the main presentation window. And with that, I would like to pass things along to Chris to get us started. So go right ahead.
Hello, my name is Christopher Leonard. I'm the Global Lead for Power and Industry at Amatech Land. I have a wealth of experience serving heavy industrial sectors, including oil and gas, power generation, metals and cement, increase efficiency, maximise productivity and drive safe operations. Decarbonisation is the largest challenge many of these global supply chains have faced. I'm keen to share the new capabilities offered by the latest temperature and emissions technology and how best practice can be shared across industries to improve performance of operations and move to a more circular and sustainable economy. For more than 70 years, Amatech Land has helped energy-intensive heavy industries improve thermal efficiency, increase product quality and control emissions. Accurate measurements are critical, now more than ever as the economy moves to a decarbonised future. High-definition thermal imaging technology, working in conjunction with portable and fixed emissions monitoring equipment, can help optimise combustion, delivering benefits including reduced fuel consumption and compliance with regulated emissions such as NOx. Complete measurement solutions from a single measurement point to high-definition radiometric thermal imaging can provide insight into critical process parameters to optimise thermal processing, ensure maximum efficiency and sustainability. The road to industrial decarbonisation is complex, has many facets and challenges for energy-intensive industries. In this webinar, we consider how to reduce CO2 emissions by reducing energy usage, maximising combustion and thermal process efficiency, and reducing waste by maximising product quality. We break this down into three areas: increasing energy efficiency, decarbonising energy supply, and capturing and storing CO2. Quick overview of the webinar content we'll be covering today. Firstly, we'll cover a quick overview of industrial decarbonisation, and then delving a little further into increasing energy efficiency, looking at decarbonising energy supplies, carbon capture, use and storage, and then some specific examples from metals, glass, thermal boiler applications, along with those from cement and mineral industries. And then towards the end, there'll be an opportunity to ask any questions. As mentioned, industrial decarbonisation is a major challenge, very complex, with many facets and some huge challenges. To make it a little easier to manage, it can be broken down into increasing energy efficiency, decarbonising energy supply, capturing carbon, its use and storage. Looking a little further into increasing energy efficiency, the key areas of focus are minimising energy use, maximising combustion and thermal process efficiency, enhancing quality and reducing emissions, getting the right product right first time, and minimising, capturing and reusing waste heat sources. Primary steel production is extremely energy intensive. Therefore, even small incremental improvements in efficiency can have large effects in terms of the carbon footprint and sustainability of the operation. In steel production, the carryover of slag into downstream processes increases the need for further intervention, reduces product quality, and produces other undesired effects. Amatech Land's slag detection system is technology specifically designed for this arduous application. It can accurately and automatically measure the steel slag ratio being poured from a ladle. This dramatically improves yields, drives higher quality product, and reduces costly downstream processing. In addition, ladle refractory wear can be reduced, increasing the payback and sustainability, as well as driving increases in operator safety. Steel is one of the most commonly used materials globally, from transport to construction. Steel is used everywhere. However, it is typically to different specifications for different uses. That may entail different chemistries, but also different thermal processing profiles. So as well as the energy used in primary production, Steel will be heated and cooled numerous times to reach the desired material properties. Typically this is done in a reheat furnace. Now, using high definition thermal imaging, we're able to give further insight into the dynamics within the reheat furnace to optimize the combustion, look at the refractory state, and extend life and avoid unexpected shutdowns. But equally as important, looking at the thermal soak of the metal products going through the reheat furnace to achieve more uniformity. This can increase yield. It can also drive quality, giving a very quick payback on investment. The high definition radiometric thermal imaging borescope, the NIR2K, available from AMETEC Land, provides levels of data and insight into processes that have never before been able to be captured. In each frame, there are almost 3 million temperature data points. That's the equivalent of almost 3 million thermocouples per image. And the imager can run at a maximum of about 36 frames per minute. So the level of data capture and the analysis that is possible enables great insight into the process and dramatically cutting fuel costs, improving product quality, and helping keep emissions within prescribed limits. I've mentioned radiometric, but what does that mean in terms of thermal imaging? This is a key point to understand so that if you're considering equipment, you understand some of the benefits and limitations that the equipment can offer. The two images shown in this slide are a non-radiometric image on the left and a radiometric image on the right. To the untrained eye, they seem similar thermal images. However, the image on the left, whilst it gives a relative temperature, cannot be relied on to give a specific temperature. So the parts of the image, say, that are indicated in white, indicating a higher temperature, are they at 1,000 degrees? Are they at 1,100 degrees? Are they at 900 degrees? It's very difficult to tell with a non-radiometric thermal imager. It just gives relative temperatures rather than absolute. Key difference with the image on the right is this is a full radiometric and calibrated image from one of AMETEC Land's thermal imagers. That means that every point within the image is calibrated to a high level of accuracy. So being able to definitively derive temperature information and use that for control systems and quality checks gives a much higher level of value. Indeed, in this particular image, with almost 3 million pixels per frame, it's the equivalent of almost 3 million thermocouples worth of data, which, if itemized and utilized in the right way, can be a very powerful tool for optimizing your process.
So now let's look at an example: glass manufacturing and glass furnaces. Glass production typically runs 24 hours a day, 7 days a week, 365 days a year. Indeed, the furnaces run constantly between essential maintenance to the time of rebuild, typically 15-20 years for a glass melt tank. This means that monitoring is required 24 hours a day, 7 days a week, 365 days a year. It's a very arduous environment, very high temperature, temperatures up around 1600 degrees. It's a highly basic environment, and that means that the instrumentation has to be heavily protected with the required engineering to make sure that it survives in such an arduous environment. The image on the right shows highly detailed data and image that we can get with the NIR2K borescope. So you've got almost 3 million pixels, or an equivalent of almost 3 million thermocouples. Because it is a radiometric image, the accuracy of each of those pixels is known within the calibration, and that makes it ideal for continuous monitoring, looking at the state of the refractories, any rat holes or potential thinning of refractory walls, And beyond that, looking at the actual movement of the product and looking to balance the combustion and burners on the left and the right, making sure that combustion is below levels where you're producing excess NOx. And that is the part of the power of the radiometric image with such high definition and detail. As can be seen from the images on the right of this slide, the advanced spectral filtering, the NIR borescope, means that the images are unaffected by the furnace atmosphere and combustion gases and deliver real temperature readings and offer the ability to clearly monitor the process and the state of the furnace. The software also offers a range of other powerful features. The images provide a massive amount of data, and being able to process that in a meaningful way is critical to gaining the full benefit. So you can correct for background reflection and continuously monitor product temperature readings. Being able to better manage the thermal flux within the glass melt tank directly relates to product quality and also the pull through, the amount of glass that you are able to pull through the furnace. Indeed, we've had instances where we've been able to increase the pull through and efficiency of a plant, reaching up to 110% of the nameplate specified capacity. And then moving on and looking at the advanced image and data processing. The image at the top is a monochrome image, which can be very good for looking at finer details within the refractory, specific, looking for the areas of thinning, rat holes or areas of cold air ingress. What you can also see in the image, the monochrome image, and to a lesser extent on the coloured image below, is a number of lines. These are called regions of interest, and what you're able to do within the software is specified lines, either straight lines, polygons, any freeform shape, and monitor the temperature along those lines, along with trends and other data processing functions. So having the appropriate software to be able to set alerts and alarms to automate part of the process, to identify critical areas and monitor those, are all areas that need to be considered when you're looking at reducing CO2, increasing efficiency, and improving product quality.
Steam methane reforming is a common process used in oil and gas applications to produce hydrogen gas from a reaction of natural gas and steam over a catalyst, typically in high nickel content tubes. Running the process just 15 degrees too high can reduce tube life by 50% and massively increase capital and running costs, while running the process just 20 degrees too cold can lead to a direct production loss of more than 2%, which is significant. With these challenges, it's imperative to understand the thermal conditions the asset is experiencing over time. This can be achieved with fixed installations that can provide permanent monitoring and can be supplemented with portable equipment to carry out periodic inspections.
As with all things, it's a case of being careful what you measure, particularly with steam methane reformers. In the first instance, selecting the right wavelength suitable for the fuel. Is the reformer fueled by natural gas? Is it fueled by tail gas? And selecting the appropriate wavelength, whether it's the NIR 2K, which is ideal for steam methane reforming fueled by natural gas, or the 3.9 medium wave MWIR-B borescope, should the methane reformer be fueled by off-gas, tail gas, or some other fuel from the reformer, which is potentially a carbonising flame. The advanced spectral filtering means that you're able to see clearly the state of the tubes, but also critical is being aware of background reflections to make sure that you are monitoring the actual tubes and areas of interest and not monitoring a reflection from another area within the furnace. So it's critical to know, that your equipment is radiometric and giving the appropriate readings, but is mounted properly and specified properly to ensure that the information that you're getting is sound and can be used to optimize, increase efficiency and improve the quality of the product, overall reducing the CO2 footprint and increasing sustainability.
Thermal power boilers are used to supply heat and power for many industrial applications. Their efficiency can be negatively impacted by a number of issues. The efficiency of a boiler can be dramatically reduced due to fouling of the tubes designed to transmit heat from the combustion to the boiler water steam system. The ability to better manage cleaning schedules can be achieved by verification using thermal imaging. The thermal imager provides data beyond that of a visual image where fouling and the impact of fouling becomes much more evident. Along with monitoring tubes and other areas of key concern for fouling, thermal imaging can also provide early warning signs for refractory damage, which enables maintenance to be more proactive and also enables further troubleshooting activities to be undertaken, maximising uptime and preventing unexpected shutdowns.
The next area of focus for today's webinar is looking at decarbonising energy supply. What does that mean? Well, the two key areas of focus: substituting fossil fuels for use with electrical power, such as using an electric arc furnace in the steel industry to produce steel from scrap rather than producing it from iron ore in a blast furnace, or replacing fossil fuels with biofuels, such as using biomass in the power industry to replace coal and other traditional hydrocarbons.
As the decarbonisation agenda increases in urgency, alternate fuels are being considered across a wide range of industrial applications. However, there's a track record already in this endeavour. The cement industry has been burning alternate fuels for many years, including industrial waste, granulated tyres, waste solvent from the chemical industry, through to various agricultural wastes. Common challenge in terms of alternate fuels is maintaining consistent supply, but also how your process may need to be modified. The amount of energy, the moisture content, the handling of alternate fuels all need to be considered. So the two areas of key focus: one is transitioning combustion. The other is in handling the alternate fuels, which we'll cover in a little further depth on the next slide. Beyond their actual combustion, one of the main considerations for converting a process to alternate fuels derived from waste or biomass is the tendency of some of these fuels to self-ignite. Therefore, additional measures may be required to ensure safe handling and storage. For instance, in the example shown below, monitoring of conveyors, silos, pulverising mills, along with monitoring of the boiler and stack, can be key requirements to ensure safe operation and handling. So just before we wrap up today, I'd just like to address a few questions that have been raised during the presentation. So starting off, the first one is decarbonisation is such a big challenge. Where do we start? It is a very complicated task. and that's why we've recommended as part of this webinar to break it down into manageable chunks. I think the best place to start is looking at the overall efficiency of your process. Modifications and changes can have not instant but very quick payback in terms of results. So that's always a very good place to start the journey of decarbonisation, is looking at the overall efficiency. High definition radiometric thermal images can be a wonderful tool to open up and shine light on a process. We've had many users comment that the thermal imaging has shown them details of processes that they thought they understood very well for many years, and given them new insight. So I think that's definitely a good place to start. The next one I think is more of a comment than a question. The equipment looks great, but surely this doesn't come cheap. As you can imagine, making sensitive instrumentation suitable for very arduous industrial environments is not a cheap exercise. However, in terms of the overall justification for that technology, what I can share with you is that various instances in terms of payback have ranged at one extreme. Payback has literally been within a matter of hours, to a typical payback on a instrumentation investment ranging from a few weeks to a few months. Typically the return on investment is high, and it justifies further investment down this path. Final question is, our equipment is designed for traditional hydrocarbons, coal and oil. How do we transition? As just touched on, looking at alternate fuels, it has been used successfully for many industrial processes, transitioning them to a decarbonised, low carbon future. However, the variance of combustion and overall process parameters means that measurement and understanding of changes to the process is a key requirement to success. A key tool in that is, again, high definition thermal imaging. It can provide data, analysis, alarms on the process that make the transition and a lot of the unknowns much closer within reach. Thank you very much for your time today. Should you have any further questions, please feel free to get in touch. My email address and phone number are shown on the screen. I can also be contacted via the AMETEK website. Thank you.
Okay, Chris, thank you for that great presentation, and thank you for choosing a few of our attendees' questions and answering them. We do have some more questions that have come in from our attendees, but we are going to answer all of those following today's webinar. A thank you to all of our audience members for being here and for being part of this webinar event, and a huge thank you to Chris for a great presentation. Take care, and we will speak with you soon.